Okay, so third and last talk of the morning. Now you'll hear a talk about detection methods that are present in both dark matter and neutrino detectors and in many of the new and ongoing experiments. So thank you, Ettore from UNICAMP.
Thank you, Martin, for the invitation. Just let me start with a bit of advertising. We are organizing another school that we think is very tightly connected with this one, and will be UNICAMP. It will be based on experimental neutrino physics. The focus will be neutrino physics. It will happen on the first weeks of December at UNICAMP. So we have the web page is this one. It is organized in collaboration with the American Physical Society. We have 100. There are 100 fellowship, let's say, because the student will be totally funded by FAPESP. So everything is paid, starting from the air ticket, the hotel, and the food. So it's totally free. We probably will need to. We need that the student pay a small fee, around $30, but all the rest is totally free. So please write on your book, on your paper, the site and apply as soon as possible. We have 100 positions. 40 or 50 will be reserved for Latin America. The other for international students. So okay. So as from the introduction from Martin, I will talk you about Nobel liquid detector and particular time projection chamber. This nowadays is a very popular detector for several reasons. Some of them are also historical reasons. Let's say why. And you know that many of the most important experiments in the particle physics now are based on these techniques, not only on neutrino physics, such as the dune, and all the zoology, all the prototypes that have been built and will be built around dune. The short neutrino baseline program, as we will see, but also many dark matter experiments. Uses time projection chamber with a different flavor. They are a bit different. Time projection chamber for dark matter and for neutrino physics. And in dark matter, they use argon or xenon, while for neutrino physics we typically use only liquid argon. So everything starts from, let's say, 50 years ago, from the bubble chambers. Many of you probably never heard about the bubble chambers, but they were a very important piece in particle physics. Mainly in experiment with fixed target, where you have a beam and you send particle on the target. This because this bubble chamber allows to have a massive detector with a significant mass, and then allows to perform a complete, perfect three-dimensional reconstruction of the event by taking exactly picture with the camera. This technology allowed many important discoveries, even based on a single event basis. By detecting a single event with a well-defined topology, they were able to make physicists were able to make important discoveries. For example, the discovery of the omega minus, or even discovery not expected with the event that were surprised with the topology that were not expected. Like, for example, the discovery of the neutral currents with the Gargamel experiment. But there is a very important technological drawback about this technique. It's very complicated. how it worked. We have a gas very compressed, very high pressure, and when you know from the spill of the beam that a particle is coming, you expand this fluid and leave it in a supercritical state. What does it mean? It means that it is in a state that is not in liquid and not gas. It needs very little amount of energy to condensate. So what happens? When the particle crosses this chamber, depositing a very thin amount of energy, the gas condensates along the track of the particle. In that moment, during this expansion, mechanical expansion, you take a picture. So you have a picture of the track of all the particles produced in this event. And they are very beautiful. Then this target is also magnetized, so that you see also the behavior with respect to the mechanical to the magnetic field. But clearly, these are very beautiful detectors, but cannot be used for modern needs. For example, for neutrino physics, because first of all, we don't know when, in case of neutrino from a beam, we know when the neutrino arrives, but for neutrino from a supernova, neutrino from atmosphere, we don't know when neutrino arrives. So we need that he understand by himself that the interaction happened inside his active volume. Then you need to have very big volumes, because as you learn from the lecture from Professor Stefan, the cross section is very small. So you need a very huge detector. So the limitation that poses the optical observation of the volume and taking a picture with the camera is not overcomable, let's say. And so physicists started to think to something different. So it was like a transition from a situation where you have an analogic camera, when you want to make a transition to a digital one. So, sorry. This is what I was talking about. This is the image from a bubble chamber. So it is perfect. The resolution is, even today, there are no detectors with the same space resolution of a bubble chamber. The TPC is near to this, but this is still better. And you see how many details. You see everything, more or less. So the idea of a bubble of the TPC is to build an electronic bubble chamber, a bubble chamber that works electronically. So just to give you an historical perspective, people started thinking to a TPC in liquid with noble liquid since the 17th or 80s. TPC were known to work in gas, clearly, but the target, if you have a target made of gas, clearly the mass is very small. So if you want more mass, you need to use liquid. And people knew that for a pure liquid, noble liquid, we will see what it means, a pure liquid. Electron can drift inside the liquid too. So why don't build a TPC with a liquid? So people start this guy Luis Alvarez in Berkeley built in the 70s a time projection chamber with xenon. It didn't work for a simple reason, that experimental particle physics always face. That is the lack of technology. So, first of all, there was a fundamental. His chamber was able to produce only a bidimensional representation of the event, and not a three-dimensional. And this is the first limitation. The second one is that the signal that he detected were very small. And what he tried to do, probably you know what is a proportional chamber. That is a chamber with a wire in the middle filled of gas. If the wire, and you know that electric field inside the chamber go like 1 over r, right? So if the field is thin enough, the electrical field near the wire is very high, and so the electron that is drifting inside the chamber can produce secondary ionization. The electron produced by this ionization will be furtherly acetylated and produce more electrons. So it is a cascade. And this process leads to an amplification of the signal. So this is a trick to overcome the problem of having small signals. So what did he try to do? He tried to do the same in liquid xenon. It didn't work, because to do the same trick in liquid xenon, or in liquid argon, what else it is, whatever it is, you need to use electric field that are not human. So you need probably an electrical, I don't know. And you have this charge all around your detector. So in liquid, so the limitation was technological, but the idea was still there, was already there. Because as Stefan pointed out in his lecture, the amount of electron that you need to detect is very small. For a millimeter of track, we have something around 5,000 electrons. People make everybody think that the liquid argon TPC were born with this paper, that is an internal note of CERN, written by the Nobel Prize Carlo Rubbia, where he proposed this idea of making a liquid argon TPC with a three-dimensional reconstruction. We will see how it is possible, and relying on a new technology, the technology of low noise electronics. So, in the meantime, the technology evolved. So, the electronic engineers invented the transistor with FET, a field effect transistor with very low noise. So they could build preamplifier to read out this very small, very tiny amount of light with a very reduced amount of noise. They, the electronic engineers measure the noise in terms of electrons. How many electrons of noise that are not related to the signal the electronics inject into the system. With this new electronics, they are at the level of 1,000 electrons of noise over a signal of, let's say, 10,000 electrons. You have what we call a signal to noise ratio that is 10. You can measure this charge in liquid because of this technological advance. How it works? Let's start from the very bottom. It is basically a capacitor, a liquid argon temperature electron chamber, where you have the anodic plane and the cathodic plane. Imagine that everything is immersed in liquid argon. Let's talk of it, focus a little bit on liquid argon. Assume that everything is immersed in liquid argon. You have a cathode, you have an anode, and you have the charge. Imagine that a particle is passing through this volume. And inside this capacitor, you apply a potential, and you create an electric field that we assume it is uniform. What happens? That if a particle crosses this volume of liquid argon, you produce electrons and ions. And they start moving because of the presence of the electric field. The electrons go toward the anodes, and the ions go toward the cathode, right? And what the work that the electric field does to move this electron is, you know perfectly, is the force that is the product of the electron charge by the electric field multiplied by the displacement. That is the velocity multiplied per delta t, per the t, where we are separating the velocity, the drift velocity of ions and of electrons. And this clearly needs to be equal to the product of the potential you apply on this very basic detector and to the current that you produce on the readout circuit multiplied by the t. So you can easily find what is the value of the current that you induce, because you are inducing a charge. The fact that the electrons are moving toward the cathode are inducing a current on the readout circuit. This is an induction current. Okay, you are inducing this the movement of the electron is inducing this current in the readout circuit. Okay, so the induction the current that you induce is equal to the electron charge multiplied by the drift velocity divided by d, and d is the distance between the plates. Okay, and if you integrate this current for the drift time, knowing that the drift velocity is v, you find what is the amount of induced charge. It is E for d minus x, where x is the position where the charge has been produced, divided by d. Very simple calculation, but they give the way to understand how small are these current. Okay, in all TPC, the contribution of the positive ions are neglected because the drift velocity of ions are order of magnitude higher than those of the electrons, so slower. So the contribution is totally negligible. So in this case, this is, you can put this to zero. If you put the right numbers here, and the number that could be interesting to remember is that the drift velocity of electron liquid argon at the proper field, that is, as Stefan mentioned before, the typical field is 500 volt per centimeter. Why? There is a reason. Is 1.5 millimeter per microsecond. What does it mean? It means that for a typical TPC that has a drift length, a distance between the cathode and the anode of the level of 1, 2, 3 meters, you take more or less, an electron take 1.5 millisecond per meter. Okay? So the detector is slow. The TPC is a slow detector because you need to wait at least one drift time to collect all the charge. You need to wait at least for, in the case of Dune, 3 meters, you need to wait for 5 milliseconds to collect everything. And why 500 volt per centimeter? I don't have the plot, but it's very easy because I can draw it here. The drift velocity of the electrons as a function of the electric field is something that is like this. It reaches some kind of saturation at around 500 volt per centimeter. So you cannot make the detector faster by applying a higher electric field because it doesn't work. The drift velocity will be always the same. So you decide to work in this point more or less where you like saturation is the best you can do in terms of drift velocity and in terms of a voltage, because an high electric field means an high potential that you need to apply, difference of potential that you need to apply to this condenser. Okay, here again need to remember that the liquid argon must be ultra pure, must be super pure. We will see what does it mean exactly to work for a TPC, for a liquid argon TPC. because now we are talking of an idealized fluid that is liquid argon. We know that argon is a noble gas that has all its electronic shells filled, and so its electronegativity is almost zero, and so the electron can move inside pure argon for an infinite time, or as we say typically, the lifetime of electron in perfectly pure argon is infinite. In real liquid argon is not, because of several reasons. So the typical current that one has for this kind of very simple detector is 0.2 divided by D in centimeter. For 1 meter is divided by 100 nanoampere. Okay, is very, very, very small current. Okay, but now our detector is simply a calorimeter. So is able only to measure the amount of charge that is deposited inside, nothing more. So let's try to do the same step that I told you before of Luis Alvarez of making a TPC. Let's try to change the plane, the anodic plane, into wires. So that what happens? Each wire will be sensitive to a small amount of the track. So you can imagine as the track is segmented into pieces, and each piece of track is sensed by the wires where it is drifting towards. Okay, so each portion of track induces a signal on the, more or less, there is clearly a crosstalk for the other wires, on the wire where it is drifting toward. And imagine that you record the signal coming for each wire. So for each wire we have a signal. For each wire the signals will be different, because let's see, because the charge will arrive at different time on each of the wires. So what happens if I take the signal from each wire and I put it one close to the other? I built an imaging detector in two dimensions. Okay, this is what happens. So you see, this is a raw signal from a real detector. These are the wires, the different wires, and this is the signal from each wire. You see that at some point you see a signal, you see a signal, you see a signal, you see a signal. If you apply finding algorithm, so you apply software filters, you pass from this picture to this one. That is one very similar to the picture that Stefan showed you before. What is it? This is a projection of the event. From here the name time projection chamber, where this is the time. So this is the coordinate along the drift, along the direction between the two plates. Because this is proportional to the coordinate, to the space coordinate, through the drift velocity that we have measured very well. We know very, very precisely what is the drift velocity. So we measure this time, we multiply by the drift velocity, and we know what is the distance of this electron packet that produced a signal on this wire. Okay, and this for all the wires. The other coordinate is the drift position. So if we go back on the previous slide, is the coordinate along this direction. So what you see on the other slide is the projection in this plane, this and drift direction, wire number, drift direction. Okay, and this is software. And other thing, as also Stefan pointed out, from the shape of the signal, for the amount of charge that you see in the signal, you know also the amount of charge that has been deposited. So you have still your calorimeter imaging calorimeter, but it's better because you can measure the d over dx, dx, because you know what is the amount of charge deposited in very small amount of tracks. This is the d of dx. You can see the beta block here, and you use it to, you will see, to discriminate particles. Is a very powerful tool. But okay, but this is only a bidimensional representation. We want a 3D. What we need to do? We need to do the same event multiple times. So we need to read out the same charge with many times with different planes. Imagine if you have this single plane that I showed you before. Imagine if you have another plane with the directional orthogonal to the direction of these wires. Imagine you have wires on this other direction. Okay? And imagine you are able to read out the charge 2 times. So you have 2 projections of the same event on 2 different coordinates with 1 common coordinate, which is the drift. The drift is always common. Okay? You have a 3D detectors if you are able to do this. And as you know, we are able because we built TPC. You need to make the first plane transparent to the charge. This is quite easy. You need to match this condition. You need to apply an electric field not only in front of the time projection chamber on the drift direction, but also behind. And the field behind the wire plane needs to be higher. Typically, needs to be double than the field you have on the wire chamber. For example, if we learn that the field needs to be is always 500 volts per centimeter. Every TPC have the same field in liquid argon. Behind the wire plane, you need to have 1 kilovolt per centimeter to make the plane transparent. This is the relation. E2 over E1 needs to be greater than 1 minus rho divided by 1 minus rho, where rho is related to the radius of the wire and the distance between the pitch. So if you put here inside, and I encourage you to do, the typical radius of these wires, that is 150 microns, and the pitch, which is 3 millimeters, you will see that this ratio needs to be 2, more or less 2. In this case, what happens? You still have on the first plane the signal induced by the movement of the electrons. This is an induction signal, and nothing changed. With the peculiarity, so you have charge coming to first wire, to the first wire plane, induces a signal. They passes, all the electron passes through the wires, and in this case what happens? That the current that you induce change side of sign, because in the first case, the plane see the charge approaching. When the charge left the plane see the charge leaving the plane. So there is a flip in the sign of the current. For this, the signal on any induction plane is bipolar. This was shown also in one of the slide by Stefan on one corner. I will point you where. The signal on each plane is different. On the first induction plane is one signal. On the second is another one. On the third one is different too, because the third in this case we have 2 planes. So in the first place an induction plane. The second plane we collect all the charge. So the signal is unipolar. Is a simple charge collector. So you see. So the last plane is always called collection plane, because it's where you collect the charge, and this is typically the best one of the planes, because you have the signal that are more sharp, where you do calorimetry and so on. Okay, I forgot you to say that this equation is not the only the end of the story, because you need to balance with the, because you want you need to balance the previous request of the ratio between electric field with the request that you want that the signals are short. So, for example, I want that in the case I have 3 planes and I have one, the first is an induction plane, the second another induction plane, the third one is a collection plane. I want that in the mid plane the signal is the shortest as possible. So the first plane needs to act as a grid for me. It needs to screen the electric field of what is away from it. And so we need to have planes that are grids and that are transparent to charge. So you need to satisfy also this condition, that is the screening, the screening power of a grid that depends on the pitch, on the rho, the parameter rho that I wrote before, on the pitch and the distance between the wet planes. So if you cross these two relations, you will find that you need to have wires with 150 micrometer in diameters, a pitch of 3 millimeters. This is not the only reason, because you need to have a pitch of 3 millimeters, and the distance between planes that is of the order of 3-4 millimeters, a ratio between electric field of the order of 2. If you match this condition, you build a 3-dimensional TPC. So here I summarized what I said. So the pitch is of the order of 3 millimeter, but there is a more fundamental reason for this, for which the pitch, the distance between wires need to be of this order. The wire radius is 150 microns. The distance between this is a mistake, 3 millimeters. So in this case, you have a 3-dimensional TPC. So, as I told you, each wire plane will give you a b-dimensional representation of the event with one common coordinate, which is the drift. There is one problem in all this. We don't know what is the T0. When did the event happen in liquid argon? Because we have a detector that is continuously sensing the charge. You are continuing collecting this charge, but when did this event happen in liquid argon? It can be any time. You need to have a T0 reference, so that you know when electron started to drift in liquid argon. You make the difference with the time of arrival, and you know exactly the absolute position along the drift. And you do this, we will say in more details, with scintillation light. Because liquid argon is one of the best scintillators we know, with many beautiful properties that are used also for dark matter, because of the property of a scintillation light. Not only because it allows to drift charge. So, as you know, the scintillation light is emitted almost instantaneously with exactly the same process that was highlighted by Stefan. This scintillator, you saw, the energy release excites singlet, triplet states in the argon. The process is more complicated, which decay emitting light. If you detect this light that is in coincident with them, you know when everything started, when charge started drifting in liquid argon. This is a T0 mark. And so you have an absolute reconstruction of the position inside the TPC. This is important because we will see why, for the energy resolution of the detector. Because in real liquid argon, when charge drift inside the liquid, they can be absorbed, and they are absorbed independently. What is the lifetime? A certain amount of charge is absorbed. No? So But you can correct for this effect if you know what is the absolute time of drift, okay? And so you can correct for the absorption. This is a general summary of what we have said. So we have a liquid argon volume. Now we know how it works. We have a ionizing track here. We have wire planes and a liquid argon volume that my liquid argon is green, with difference with the Stefan one. So you have a series of wire planes oriented in different directions. So the charge is drifted toward the wires. You collect the signal from the first plane, from the second one, and for the third plane. So simultaneously, you detect the scintillation light. You have the T0 mark. You have the drift time. So you have the drift position, and your detector can work as a three-dimensional camera. Why the signal are different? Probably you notice that in one of the slides of Stefan, there was on the right corner something like this. Okay. The red one is the signal from the first induction plane. It is bipolar because it is an induction signal, but it is unbalanced. It is smaller here and bigger here. Why? Because of this relation that I showed in the first slide, that the current is equal to the charge multiplied by the drift velocity divided by the distance between the planes. So when the charge arrives in the first induction plane, the distance between planes is 2 meters, 3 meters. So V over D is small. So the current is small. When the charge crosses the first induction plane, the distance between the first and second induction plane is much smaller, order of centimeter. So V over D, even if the electric field is higher, but we understood that the drift velocity do not change, but the distance is smaller, so the current is higher. So for this reason, the signal in the first induction plane is unbalanced. So you have a smaller current here and a bigger after. For the second induction plane, that is the blue one, this does not happen, because it is in a sandwich between the first plane, the induction plane, and the third plane, that is the collection plane, and the distance between the two is the same. So the current is the same before and after. So is a perfectly symmetric. And this is the collection signal, because this is not an induction signal, but here you collect the charge, is higher than the other two, is bigger, and is unipolar. So you have 3 different signals for each plane. Then what you do with the signal is your business. So you can read out with an integrator, with the semi-integrator, take any time as you prefer, but this is the signal that you obtain from the chamber. So, yes? Because the first two are induction signals, while the third one is a collection signal. You make, for example, behind the third plane, you don't have an electric field. Charge ends up in the wires. They don't have, there is no reason for which they need to go away, because there is no electric field behind the wires. Is the same. It's exactly the same. Are different? Bias. Yes, they are. Yeah. But in any case, here you collect the signal, all the charge, and the other plane not. This is the main difference. Okay. So just to summarize what we said, so why liquid argon? So ideally it is a perfectly dielectric medium. It is a quite high electromobility, as we saw. It can be, this is one of the most important things to make the TPC work. It can be purified at very high levels. Now we will see how. It has a quite high electron pairs, pi yield, about 10,000 electrons for 2 millimeter of ammonium ionizing tracker produced, and probably the most important reason, it is quite cheap, because it is extracted from air, because about 1% of air is made by argon. So in the process of when you liquefy air, the argon is a byproduct to produce oxygen, typically. And here you can see I summarized a few of the physical properties of the liquid argon. But because it is a byproduct, the argon that you buy on the market is not pure enough to work in a TPC. Just let me, before going into this, just let me show you how the signals are read out. So each wire has its own electronic channel. So if you have a chamber with 50,000 wires, you have 50,000 electronic channels. For this reason, you need to have the drift distance as large as possible, because you want to minimize the number of wires. If you want a detector with a 3 meter drift length and you divide the chamber into two, that you can do, that has been done, you double the number of the wires. Even if things probably work better, is less demanding in terms of purity, but you need to double the number of chambers. That is a cost, not only economic, but also a technological effort. Storing the data produces a lot of issues. So you have the wire. The signal is preamplified with very low noise preamplified. It is shaped, if you want, and then it is digitized. And then it is stored on a circular buffer. It continues, this chamber typically continually store signals, and when they receive a trigger, there can be the light of the flash of the light, the scintillation light, they download the buffer and they write somewhere, because this is there is an event. So why the ramos of drift length? Oh, as I told you, there are several reasons that in the drift length that influence the design of a TPC. Good. The first one, okay, we already go through this. You want to minimize the number of wire planes, so you want to increase the drift length as much as possible. You go into some troubles also in this case, because in having a higher drift length, you need to have a higher voltage between the cathode and the anode. So for a 3 meter, if you want a 500 volt per centimeter electric field in a 3 meter chamber, you need a power supply. You need to supply 150 kilovolt. That is a huge potential, and many experiments had issues already with this because you know that if you put high voltage and argon together, the easiest result is a discharge. So you need to pay a lot of attention when you build something that goes in liquid argon, in argon in general, with 150 kilovolt. And then there is the diffusion of the electrons, because I assume also even that you are able to make a potential as big as you want. Then you go into trouble with the resolution of your image, because the electrons clearly, while drifting, and even when they don't drift, they diffuse. If you produce a bunch of electrons in a place, they start diffusing. There is no way. And this happens also when they drift. And you know that the Einstein relation is this one for the distribution is approximately Gaussian, and the sigma is the square root of 2d multiplied by t, where d, the diffusion coefficient, is about 5 square centimeter per second. What does it mean on a scale of our 3 milliseconds of drift of the charge? That it results in a smearing of the dot of the order of millimeters. This drives also the determines the distance between the wires. That is of the order of millimeters, 2, 3 millimeters, 5 millimeters, because there is no gain in putting wires closer. You don't gain resolution because the physics is limiting your resolution. You can do anything about this, almost anything. And then there is the other trouble in which you go by augmenting the drift distance, is the electron attachment probability. That is, electrons drifting in real argon are attached. No matter, depending on the purity of the argon, they are more or less attached, but they are attached. Let's try to understand what level of purity we need to make it work. It is very easy. The principle is very easy, because the variation of the population of our electron is proportional to the concentration of electronegative contaminants. The electronegative contaminants attach the electron, they eat the electron. And the most efficient one is the oxygen. Is the NMI number 1 of a TPC is oxygen. No, there is no doubt on this. So this is a very simple equation that all of you know how to solve. It is an exponential. So the electron density varies exponentially with the characteristic time, which is with an inverse characteristic time, which is proportional to the reaction constant and the concentration of oxygen. Okay. What is the we need to put the number in place to understand things in when you build a detector. So what is the value of the number? Is about 2 ppm minus 1 microseconds and minus 1. What does it mean? Liquid argon that you buy on the market, if you call Air Liquide or call Linde, bring to me the best liquid argon that you have. It comes with the dewar, and you have a liquid argon that has a purity at the level of 1-2 ppm. You would like to build a TPC with this argon, you put the liquid argon, you see it doesn't work. Because you need much better. And you understand from this relation. So if you want, if you put the number here, if you want a lifetime significantly higher of 1 millisecond, you need to have a concentration of oxygen below 1 ppb. So you need to do something, because what you buy is not good. You need to improve the purity of liquid argon by 3 orders of magnitude, at least. to have a lifetime of 1 millisecond. That is very poor. So what these detectors do is they purify the liquid argon continuously. There are pumps that are installed inside liquid argon that push the liquid inside the filters. The working principle is very easy. It is copper. They are made mainly of copper. The filters that capture oxygen are made of copper, but copper that is activated. Because copper oxidate, reacts with oxygen very efficiently, and it is eating all the oxygen from the liquid argon. You take the filter are very big, typically 100 of kilos of coppers for these big detectors. They make in powder to increase the contact surface between liquid argon and the copper itself. It needs to be activated because the copper that you buy is already oxidated. It oxidates immediately. So you need to put in an oven. You need to heat this oven at 300 degrees. You go inside these filters filled of oxide copper with a mixture of hydrogen and argon, typically a mixture of 5% between hydrogen and argon. Hydrogen reacts with oxygen and produce water, which you push away with the argon, with the flux of argon. So with this process, the process you need to start working at about 300 degrees. So you need to have a big oven where you put this filter. After this procedure, the filter is ready to work with a liquid argon detector. So, and you start circulating your liquid argon inside this filter many times, and the purity start going up, and you at one point you will start looking. You will be able to see some signal. So, how do you measure the purity of liquid argon? We use one of the tools. Is this one? Is a purity monitor that is very small. It's a small drift chamber. You substantially what you do? You produce electrons. You make the drift for a distance. You measure how many you produced, and then you measure them at the end of the drift. This is and so you know what is the lifetime of the electrons. You produce the electron here. You have an optical fiber going here on a photocathode. You use UV light to extract electrons, a very strong UV light, xenon light. Then you apply an electric field. You put a grid here, so when the electron pass for the same principle or temperature chamber, they induce a signal. You detect this signal. The electron drift up to the anode. Here there is another grid. You induce another signal, but the number of electrons is smaller, so the signal is smaller. But the ratio of these two signals, you know what is the lifetime. Some of these are installed in many liquid argon TPC. And so when the detector is working, you measure the lifetime and you obtain something like this. For a good detector, here you have a lifetime that is of the order of 10 milliseconds. But if the pump stops working, you see that you lose your purity, your lifetime more or less instantaneously. And then when you restart the pump, you need some time to recover your lifetime. But the pumps need to always operate, because there are a lot of things inside the chamber that emit oxygen. The cables, the first thing are the cables that are full of air. So they inside, and they are in the hot part of the detector, because you read out the signal with the cables. The cables need to go out. So at some point there is a flange where there is the gaseous phase of argon. This is the hottest part of the cryostat, and where this process of wires emitting continuously oxygen happens, contaminating argon. So you need continuously to purify your liquid, your liquid. So, okay. Let me in this last part of this lecture talk about this scintillation light, because this will be the link with dark matter detectors. As I told you, in this chamber, the T0 signal, the time at which the event occurred, is given by the flash of the light. That is more or less instantaneous. The process of emission of scintillation light is in competition with the charge collection. Because clearly, if you don't apply any kind of electric field, the charge would recombine with ions and will emit more light. So applying the electric field prevents electron and ions from recombining, so you lose a fraction of the light. So the sum of the photons and of the electron more or less is 1. So if you use charge, you lose light. So they are perfectly complementary. The working point, so this is the fraction, the fraction of energy which goes in light, and this is what goes in charge. And at 500 volt per centimeter, we are more or less here. We are more or less 50% of charge, 50% of light. So what happens? When there is an ionizing event in liquid argon, you produce both ions electron couples and excited argon atoms. Both of them ends up in a state which is an excimer. That means an excited dimer. The argon form a molecule. In their fundamental state, argon atoms don't form molecules because they have their electronic shell completely filled, so they don't need to make any kind of connection to decrease the total amount of the total energy. But when they are in excited states, there are state of aggregated atom, of two aggregated atoms that are more economic in terms of total energy. So excited argon molecules exist, and they're called excimers. It's called excimer over excited dimer. So what emits scintillation light is not exactly the argon atom, but is the argon excimer, argon 2 star. But exactly as in the same way as shown by Stefan before, this excimer goes into excited state, which can be singlet state or a triplet state. The fundamental state is a singlet state. So the transition from this state to the fundamental state, that is two atoms that are separated, is instantaneous, the order of few nanoseconds, because it is a transition between two singlet states. When the excimer is in a triplet state, the transition to the ground state is forbidden by selection rules, as you know. So this transition is much slower, order of microseconds. And this is a very important point for dark matter experiment, because this is what generates the discrimination power of liquid argon in terms of pulse shape. Because what is the shape of this? Okay, we will see this in the next slide. Other problem is that the wavelength of the photon is in the vacuum ultraviolet. Is 128 nanometer. Is very energetic. It's about 10 electron volt. And it is very difficult to be detected because all the windows, this is another technological problem, the windows of the photomultiplier or the photon detector are made at the best by quartz or fused silica, that is a synthetic version of the quartz. And it is not transparent to this wavelength because it is transparent down to 160 nanometers. So in the case of liquid xenon, it can work because the emission wavelength of liquid xenon is 174, we're fine. But for liquid argon, we have to invent something different because this detector doesn't work. Then, the photon yield is quite high, is about 440,000 photons per MeV of energy deposited, with the slight dependence on the type of particle which produces the ionization. So what is the shape of the signal? As you know, as the result of this decay from the singlet or triple state, you have two exponentially decaying components. One which is very fast, with decay time of the order of 6 nanoseconds, and the other one that is much slower, with the decay time which can be of the order of 1.5 microseconds. What you use this property because you have two very different populations. One with a very fast decay time, one with very slow. The nice thing is that the relative abundances of these components depend on the particle which produces this excitation. So the shape of the signal for different particles are very different. This allows you to very well discriminate electrons from neutrons, for example, or neutron for alpha particles, electron from alpha particles. And this is the source of the more or less quite all the discrimination power of liquid argon detector for dark matters. And we will see this tomorrow. To detect this light, we need, as I told you, we need to make something different. So we need to change the wavelength of this light because there are materials which are transparent to this light, but they're very expensive. So what we commonly do, we cover, for example, our detector of light with materials which are typical organic, which absorb this light with high efficiency and re-emit in the visible. The most popular is this one, is the tetraphenylbutadiene, that is commonly called TPB, which absorbs UV light and emits at 430 nanometers. It is exactly, again, the same process of excitation, absorption of the photon, excitation in this case, if there is no ionization, to a singlet state, which decays more or less instantaneously to the ground state, with the decay time of the order of this molecular transition 1 to 2 nanoseconds. So this conversion is instantaneous. So you put UV photon and you obtain blue ones, which are more easier to detect, and more or less all the detectors that you for neutrino, for dark matter, use this material. This is a fundamental piece of the detector, especially in dark matter, because without this thin film of material, they cannot easily operate. And this is something that sometimes a little bit forgotten. I think I can stop here. Let me see. Okay. Let's stop here. So then tomorrow we will go on with something more about scintillation light, and then with dark matter, dark matter flavors of TPC.
So we can take a couple of questions.
On the wires and on when you measure the signal, there is no electron loss or crosstalk between the wires or problems like this?
Yeah, there is something of this clearly. They are because the wires are not screened perfectly one from the other, but the amount, especially in the not the first plane, the other one, the distance of drift is so small that this effect is very, very minimized. But there is some of this clearly.
Other question?
How do you detect light if the wires will act as a Faraday cage?
But there is no. The only problem with wires is that they screen your detect because you put the light detector behind the wires. But the fact that it's a Faraday cage doesn't imply any loss of light. There is the effect of the screening of the wires with respect to the photon to the photons, but there is any kind of you lose photons because of this electric field because you collect charge and you lose light, but there is no any other drawback in detecting photons.
Okay, so I have a very good news that the experiments are working, and that's amazing. I mean, yeah, it's so complicated to have everything here and working. So, of course, there's a team that's been working for the past week, and everyone was working on the weekend, every day, all the day long, Saturday and Sunday to make that work. But still, it's amazing that it is working. And after after lunch, you know which experiments were assigned to you. You know, as we said, unfortunately, it's not possible to satisfy all the 5 preferred experiments.
But the good news is that the 3 first options are mostly respected.
Okay, so great. So
Everybody will do the first 3 options, at least.
fantastic.
Both the last.
And we reconvene at 2:15, so it's a bit earlier than last week. So beware of the time for lunch. So at 2:15 we are back. Thanks. And let's thank again the speaker.